Dear students, in this video from magnetic effects of current, we will study dipole moment of a revolving electron, bar magnet, its behavior in magnetic field and Earth's magnetic field. So let us begin with bar magnet, and you all must have seen it. A bar magnet has two poles, north pole and south pole. So I'll show it here. The poles have pole strength M each, and the poles are situated slightly inside the edges. So the distance between them, called magnetic length, is lesser than the actual length of the dipole. So the magnetic length and geometric length, right? Now, the ratio of magnetic length and geometric length is nearly 0.84. We can easily compare this dipole with electric dipole. So, if we have electric dipole consisting of minus Q and plus Q, then we can compare the south pole with negative charge, north pole with positive charge. The pole strength is compared with magnitude of charge. This is also magnitude of charge, and the dipole moment, which is directed from negative charge to positive charge, is compared with magnetic dipole moment. So we have electric dipole moment from minus Q to plus Q and magnetic dipole moment from south pole to north pole. Their magnitudes are also similar. So there is clear analogy between electric dipole and magnetic dipole. Now, magnetic monopoles do not exist. Now, what does that mean? If we have a magnet consisting of north pole, south pole with some dipole strength and pole strength, and it is broken into many parts, say we have shown 3 parts here, then you can see that new poles are created. So here a south pole is created. In this part, a north pole and south pole is created. Here again a north pole is created, and they all have same dipole strength. So we have created many magnets of equal pole strength, right? So you keep on breaking it into smaller and smaller parts, and each part will behave as a magnetic dipole or a magnet. So even when we reach the atomic level, then each atom will behave as a magnetic dipole. We cannot separate north pole and south pole. So we do not get monopoles, right? So we do not have magnetic monopoles. But in case of electric dipole, we can easily separate the charges. And now, definition of magnetic dipole moment. It is a vector directed from south pole to north pole. Its magnitude is product of pole strength M and separation 2L. So M is equal to M into 2L. It is similar to electric dipole moment Q into 2L. And the SI unit of pole strength is ampere meter, right? And SI unit of magnetic dipole moment is ampere meter square. So now let us talk about Coulomb's law in magnetism. And here, the force between two magnetic poles is directly proportional to product of their pole strengths and inversely proportional to square of the distance between them and acts along the line joining the poles. So it is similar to Coulomb's law in electrostatics. We have two poles with pole strength M1, M2. Separation between them is R, and the magnetic force between them is proportional to M1, M2 upon R square. And when you put equality sign, the constant is mu naught upon 4 pi M1, M2 upon R square. And you can compare it with electrostatic force between two charges, that is 1 upon 4 pi epsilon naught Q1 Q2 upon R square. And you can see that the constant is replaced by 1 upon 4 pi epsilon naught and the pole strengths are replaced by the charges and the separation. So there is clear analogy between them. And now, as in electrostatic force, the magnetic forces are also conservative forces and they are also central forces. And central forces means the forces act along the line joining the poles. Now let us talk about magnetic field lines. So definition first. They are paths followed by imaginary isolated north pole in a magnetic field. See, we cannot have an isolated north pole. Magnetic monopoles do not exist. But if we had an isolated north pole, then the path followed by it in a magnetic field will be called magnetic field line. And characteristics of magnetic field lines. Number 1, magnetic field lines are closed continuous curves. So let us see how. If you have a magnet, north pole, south pole, then the magnetic field lines form closed continuous curves. And magnetic field lines start from north pole and enter into south pole, and inside the magnet they are from south pole to north pole. Outside start from north pole, enter the south pole, inside they are from south pole to north pole. Another path you can see. So the path followed by the magnetic field lines, you see, like this one, and you see outside the magnetic field lines are from north pole to south pole, inside from south pole to north pole. Unlike in electric field lines do not form closed continuous curves. They form continuous curves but not closed. That's an important difference between electric field lines and magnetic field lines. So let us move to the next point. Tangent drawn to magnetic field line at any point gives the direction of magnetic field at that point. So if you choose any point, at this point the direction of magnetic field is this, at this point direction of magnetic field is this, and so on. So tangent shows the direction of magnetic field. Now the next point. Two magnetic field lines never cross, and if they happen to do so, there will be two directions of magnetic field line at the point of intersection. So it is not possible. Now just try to understand. If we have two magnetic field lines crossing like this, then at the point of intersection, see, we can draw tangents like this and a tangent like this, right? So we have two magnetic field lines B1 and B2 at this point. So which is not possible. We can have only one magnetic field at one point. So two magnetic field lines never cross each other. And magnetic field at an axial point of a bar magnet. You have done similar problem for electric dipole. So we have a bar magnet or magnetic dipole consisting of south pole, north pole, pole strengths M, magnetic dipole moment capital M, the size of a magnet is 2L, and on axial point at point P at distance R, we wish to find out the magnetic field. Okay. Its distance from north pole is R minus L and distance from south pole is R plus L. Right, you can see. See, this distance will be R minus L and this distance will be R plus L. Right. Now, at point P, you will have magnetic field due to north pole which will be directed away from it. Magnetic field is always directed away from north pole. And you will have magnetic field due to south pole which will be directed towards it. Magnetic field due to south pole is always directed towards it. So, let's see. The magnetic field due to south pole Bs, magnetic field due to north pole Bn. And since north pole is closer to this point, the magnetic field Bn is larger than Bs, and the vector sum of these two will be along the direction of the bigger vector. So, the direction of resultant magnetic field B is along the bigger vector, and now if you see, the direction of this resultant magnetic field is same as the direction of this magnetic dipole moment. So, this magnetic field is directed along the direction of magnetic dipole moment. And now let us look at its mathematical part. So, at point P, magnetic field due to south pole Bs is mu naught upon 4 pi m upon R plus L square. See, it is similar to electric field, that is 1 upon 4 pi epsilon naught q upon R square. So, you can compare and remember these formulae. So, now magnetic field at point P due to north pole is mu naught upon 4 pi m upon R minus L square. See, the distance from north pole is R minus L. And the resultant magnetic field is vector sum of these two magnetic fields, and the magnitude is Bn minus Bs. So, putting the values of Bs and Bn in this equation and simplifying, we get this result as mu naught upon 4 pi 2m upon r cube. Now, what is this m? This m is magnetic dipole moment, m into 2l. And also, the size of the magnet is considered to be much smaller than distance of point P. So, this relation is also similar to electric field due to an electric dipole, that is E upon is equal to 1 upon 4 pi epsilon naught 2p upon r cube. So, it is easy to remember and take care of the directions. Now, this again is a problem similar to that of electric dipole. So, magnetic field at an equatorial point of bar magnet. So, here we have a bar magnet with pole strengths M and dipole moment M. The size of magnet is 2L, and at distance R lies the point on equatorial line and the magnetic field from north pole is directed away from it at point P, and which is named Bn, and magnetic field at point P is directed towards the south pole, you can see. And at this point we have two vectors Bs and Bn, and we have to find out their vector sum. Now this side is L and this side is R. So using Pythagoras theorem, the distance of this point from north pole is under root L square plus R square, and same is the distance from south pole. Okay, and now how do we find out the resultant of these two vectors? So what we do is, if this angle is theta, then this angle will also be theta, and this angle is also theta, and this angle is also theta. So these two are alternate angles, these two are corresponding angles. And now we will resolve this vector and this vector along this equatorial line and perpendicular to equatorial line. So resolving Bn, we get Bn cos theta and Bn sin theta. See, the component along this axis is Bn cos theta, and along the equatorial line is Bn sin theta. You know that the angle with the theta is cos, and angle away from, the component away from theta is sin. So that is easy to remember. Similarly, the components of Bs is Bs cos theta and Bs sin theta. So the component with the angle is cos and away from the angle is sin, and magnitude of Bs and Bn are equal. So Bn sin theta is equal and opposite to Bs sin theta, so they cancel out, and we are left with just these two components. So the resultant is along this direction, the resultant magnetic field is along this direction, which is opposite to this magnetic dipole moment, and the value of cos theta we need to find out. See, this angle is also theta, so cos theta will be equal to this side base upon hypotenuse, that is L upon under root L square plus R square. So keeping all that in mind, the solution here, the magnetic field due to south pole is mu naught upon 4 pi m upon R square plus L square. See here, R is under root L square plus R square, and इस पूरे का भी square करोगे तो square root is gone. And same is the magnitude of magnetic field due to north pole. And now the resultant is vector sum of Bn and Bs, which is equal to 2 Bn cos theta magnitude. And now see, putting the value of cos theta as I explained to you, and putting m is equal to m into 2L, we will get magnetic field like this, considering that L is much smaller than R. Approximation case. It is similar case as we have done for electric dipole. And important point to note here is that the resultant magnetic field is anti-parallel to magnetic dipole moment. So in vector form, the magnetic field B is minus mu naught upon 4 pi m upon R cube. B and m are anti-parallel. So easy problem. Now talk on a bar magnet in uniform magnetic field. We have uniform magnetic field and a magnet is placed in it of size 2L and pole strengths m and magnetic dipole moment m at an angle theta with the magnetic field. And now each pole will experience force due to this magnetic field. Now the force on north pole is along the direction of magnetic field, which is equal to Mb. So F1 is equal to Mb. And force on south pole is opposite to the direction of magnetic field. So it is going to be along this direction. Let's see. F2 is equal to minus Mb. Now, this F1 and F2 are equal and opposite in magnitude, but they have different line of action, you can see. So as a result, they will try to rotate the magnet in clockwise direction like this. So we wish to find out the torque acting on the magnet. See, F1 and F2 form a couple. So if I produce this line here and this is F1, so the distance between the line of action of F1 and F2 is this much. So which is 2L sine theta. You can see that the separation between the two lines is going to be 2L sine theta. If this angle is theta, this is also, then this is also theta, and this side will be 2L sine theta. Okay. So see, force on north pole F1 is Mb, on south pole minus Mb. Net force is 0. That means there is no translational motion. That means the magnet cannot have linear motion because net force is 0. And now see, F1 and F2 make a couple and they apply torque on this magnet to rotate the magnet clockwise. Now the value of this torque is given by force into perpendicular distance between the forces, and force is Mb. The perpendicular distance is 2L sine theta here, and just rearranging 2 ml into B sine theta, and this is equal to magnetic dipole moment. So we get Mb sine theta. So what we get is, we get torque is equal to Mb sine theta. This is magnitude of torque, but torque is a vector quantity. So the vector form of this relation is torque is equal to M cross B. And using the right hand screw rule, you can see that direction of M is this, direction of B is this, angle between them is theta, and using right hand screw rule, you can see that the torque will be directed normal to the plane of this paper or screen and inwards, and it will tend to rotate the dipole in clockwise sense. Okay, and now some special cases here. See, when theta is 0 or 180 degree, since this sine theta will become 0, so torque will become 0. And see what happens. A situation like this. When theta is 0, that means M and B are parallel, and in this situation torque is 0, force is 0, and the magnet is in stable equilibrium. And in this case, the magnetic dipole moment is anti-parallel to magnetic field. So net force on this is 0, net torque on it is 0, and it is in unstable equilibrium. And now when theta is 90 degree, then the value of sine theta is 1, and the torque acting on it becomes maximum, which is equal to Mb. And so when the magnet is placed perpendicular to magnetic field, it experiences maximum turning effect or maximum torque. Now, potential energy of a bar magnet placed in uniform magnetic field. So if we have uniform magnetic field B and a magnet is placed in this magnetic field with pole strength M, magnetic dipole moment M at an angle theta 1. The forces on the poles are F1B and minus F2. F2 is equal to minus MB. See, this is inverted. F2 is equal to minus MB. Okay. So, the magnet will tend to rotate like this in clockwise direction. It is placed at an angle theta. Now, what we do is we apply an opposite torque and rotate the magnet opposite to this torque. So, let's see what happens. The magnet is rotated opposite to this torque up to angle theta 2. So, the magnet has tendency to turn this way and we apply opposite torque to rotate it. So, that means some external work is being done on it. Now, this work done gets stored in it as its potential energy, magnetic potential energy, and we are going to find that out. So, the work done in rotating the magnetic dipole against torque in a magnetic field gets stored as its potential energy, and we are going to find out this work done. So, here you know that the small work done dW is equal to tau d theta, and we are rotating it from theta 1 to theta 2. So, the total work done is integration of dW or integration of tau d theta from theta 1 to theta 2, and putting the value of torque, which is mb sin theta, from theta 1 to theta 2. mb is constant outside. Integration of sin theta d theta, and integration of sin theta is minus cos theta. So, here we'll find out the value of cos theta from lower limit theta 1 to upper limit theta 2. So, putting the values, upper limit minus lower limit, this work done is potential energy U, mb cos theta 1 minus cos theta 2. This is general relation for potential energy of this bar magnet. And in a special case, when initial position theta 1 is taken as 90 degree, then cos theta 1 will become 0 as cos 90 is 0, and theta 2 is taken as theta. So, cos theta 2 becomes minus cos theta, and then the relation becomes U is equal to minus mb cos theta or minus m dot b, scalar product of magnetic dipole moment and magnetic field. And it is similar to potential energy of an electric dipole, which is minus p dot E. So, you can compare these two relations. Now, we move on to dipole moment of a revolving electron or atom as a magnetic dipole. So, let us consider orbit of an electron in an atom of radius r. An electron is revolving with velocity v in its orbit. So, when the electron is revolving like this, it can be treated as a current loop in opposite direction. The current is opposite to direction of flow of electron. So, you can see the current is anti-clockwise and electron is moving clockwise. So, here revolving electron in its orbit will give a current loop, and time period of revolution of electron is 2 pi r upon v, circumference upon velocity. Now current is charge upon time. Charge is E, time 2 pi r upon v. Simplify it, you get this. Now magnetic moment of this current loop is current into area IA. Put the value of current from here, EV upon 2 pi r. Area of the loop is pi r square. It is equal to EV upon 2. So the magnetic dipole moment of this current loop becomes EVR upon 2. And now we are going to find out another form of it. You see, the angular momentum is given by L is equal to R cross P, where P is linear momentum and linear momentum is mv. So its magnitude is mvr. And according to Bohr's quantization condition, for an electron to be in stable orbit, its angular momentum should be integral multiple of h upon 2 pi. You all have done this Bohr's quantization condition, you see. So the angular momentum of electron is integral multiple of h upon 2 pi, right? And in the first orbit, this n is taken as 1. So putting the value of L is equal to mvr equal to nh upon 2 pi. See what we get. mvr is equal to h upon 2 pi. From here, vr is equal to h upon 2 pi m. Bring this m to this place. And now, magnetic dipole moment is EVR upon 2. We just found out, just see. M is EVR upon 2. Putting it here, M is EVR upon 2. Now, here. E upon 2 here, and VR from this relation is h upon 2 pi m, and simplify it, you get EH upon 4 pi m. Now you see, E is charge on electron, H is Planck's constant, 4 pi, and m is mass of electron. So this quantity is a constant, and this constant is called Bohr's magneton. This is magnetic dipole moment of hydrogen atom in its first orbit, and its value comes out to be 9.27 into 10 raised to the power minus 24 ampere meter square. Bohr's magneton. Now let us look at Earth's magnetic field. Earth is spherical, you know, and it revolves around its geographic north-south axis. You know that it revolves like this, but the magnetic north-south is slightly away from it. This magnetic north lies somewhere in Canada, and this goes in Antarctica, and the angle between them is about 11 to 19 degrees, and you have this great circle equator. We call it geographical equatorial plane, and you know that when a magnet is hanged freely, it always rests along north-south direction, and the north of the magnet always direct towards the north. So we imagine that there is a big magnet buried inside Earth with its south towards magnetic north and north towards magnetic south. We imagine that this north is attracted to this south pole and this south pole is attracted to this north pole. See, in reality, it is not possible to have a magnet inside the Earth, but it is just a simplistic picture to understand the Earth's magnetic field. So now the angle between this magnetic axis and geographic axis is theta, and magnetic field lines start from North Pole and they enter the South Pole like this. See, starting from North Pole and entering the South Pole. Okay, similarly on the other side, starting from North Pole, entering the South Pole. Okay, and one more interesting thing to note is, if you are standing on this North Pole, so if your head is like this and legs this, then the magnetic field lines will be entering through your head vertically downwards. And if you are standing on the South Pole, then the magnetic field lines will be going out vertically upwards. And if you are here at equator, see, this perpendicular line to magnetic north south is called magnetic axis, and here, and if we look at a great circle along it, then it is called magnetic equator. Okay, so we have magnetic equator here, and when you are at magnetic equator, the magnetic field line is parallel to the Earth's surface, so it is horizontal here. It is horizontal here, magnetic field lines. Okay, the Earth's magnetic field is very small. It is of the order of 10 raised to the power minus 4 Tesla, and you see magnetic equator as I have shown you. So now some definitions. Geographic meridian is vertical plane containing geographic north-south at any place. So if you have a vertical plane containing the North Pole and South Pole, geographic north-south pole, then that will be called geographic meridian. And geographic equator, it is the great circle on the axis of the earth, on the surface of the earth, in a plane perpendicular to geographic axis. Now magnetic meridian, at any place it is a vertical plane passing through magnetic north-south poles of the earth. And we have magnetic equator, as I discussed, is a great circle on the surface of the earth in a plane perpendicular to magnetic axis. And Earth's magnetic field can be represented by 3 elements. So they are called elements of Earth's magnetic field. So if we have geographic meridian like this and magnetic meridian, and the angle between them is this theta, then this angle is called declination. Angle between magnetic meridian and geographic meridian is called declination. The angle between magnetic meridian and geographic meridian at a place is called declination, and it varies from place to place. So it does not remain constant. Now, dip or inclination. See, magnetic field is always slightly bent. So the angle which it makes with the horizontal is called angle of dip in magnetic meridian. If this is horizontal direction and if this is magnetic field in magnetic meridian, then this angle will be called dip, represented by delta, or inclination. Okay. So the angle between horizontal component of Earth's magnetic field and Earth's resultant magnetic field at a place is called dip or inclination. Now it is 0 at equator. You see that at equator the magnetic field line is horizontal. So angle of dip is 0, and it is 90 degree at poles. See, at poles the magnetic field is vertical, so angle of dip is 90 degree. And the third element is horizontal component of Earth's magnetic field. So these three are called elements of Earth's magnetic field. And now relation for Earth's magnetic field. So here you see, if B is the magnetic field at any point and it makes angle delta with the horizontal, then the horizontal component of Earth's magnetic field is BH, vertical component is BV, and this angle is angle of dip in magnetic meridian. Then clearly this BH is B cos delta, BV is B sin delta, and tan delta is, divide this by this, BV upon BH, and the resultant magnetic field is under root BH square plus BV square. So in the board exam, you get numerical problems based on this tan delta or this one or these formulae. Also the elements of magnetic field, elements of Earth's magnetic field are asked. So with this, I reach the end of this video. Thank you for watching.